Our topic today is measuring, and we're going to start with just a little observation by D.J. Finney. The number 3.8 tells us nothing beyond the numerical significance of 3.8. 3.8% fat in milk, or 3.8 kilograms as a birth weight of a baby, conveys additional information. Anyone who doubts this assertion, that putting units to the number conveys additional information, should try the consequences of reading 0.8 or 12.8 for 3.8. So let's experiment a little bit. 0.8, well, 0.8, 3.8, 12.8, doesn't really matter. But what about 0.8 fat in milk as opposed to 3.8% or 12.8% fat in milk? What about 0.8 kilograms as a birth weight instead of 3.8 kilograms or 12.8 kilograms as a birth weight? We're going to do a quick check first of all. This little discussion of measurement and the significance of numbers should be enough to get you started. So what I'd like for you to do is to turn the lecture off for a few minutes, see if you can match the correct term to its definition as given below. When you've done that, turn the lecture back on and check your work. Hopefully our brief introduction and thought-provoking experiment there was enough to let you to help you get these correct answers. Hopefully you noticed that to measure is to assign a number to some property of an individual. That individual can be a person or a thing. Numerical variable is the result of measuring some property of individuals that is different in each individual. So since the value for that property varies from individual to individual, the result of a measurement, repeated measurements of different individuals, is a numerical variable. An instrument is used to make measurements. Sometimes it's a yardstick, sometimes it's a scale. There are many other things that can be used as instruments. Sometimes it's a rain gauge. Just a few examples of instruments. And finally, that leaves units of measurements that can often choose, that we can often choose which one of those to use. We can choose to measure in centimeters or inches or feet or yards, for example. We're going to take a look at a few examples in this lecture, as we often do, and talk about this idea of measurement. Some of the problems it poses, some of the questions that must be answered. Variables must be exactly defined. Measurement is a process that assigns numbers to represent constructs like height, like weight. Those are some of the easy ones. Like happiness, like fulfillment. Those are some of the more difficult ones to measure. Exactly defining a variable is often done operationally. That is, we specify how the variable is to be measured. That's how we define the variable that we are collecting. Let's take a look at this example. A local health club is doing a survey to see if there is a relationship between strength and fitness. They want to measure the strength and fitness of a sample of 100 members of the club. Which of these two attributes do you think will be easier for them to measure? Well, it would be a lot easier to measure the performance of a task. So for example, if we wanted to measure strength, all we'd have to do is record how much, what is the largest weight that a person can lift without injuring themselves. Fitness, on the other hand, is rather vague. Some traits, such as fitness, are not easy to measure at all. We have to stick to measurable constructs, like the performance of certain tasks. We can measure strength by recording the heaviest weight an individual can lift. We cannot measure fitness so easily. After all, what is fitness? We'd have to define it first and then find ways to measure it. The next example is interesting. Does the length of the lifeline on the palm of your hand measure your life expectancy? So that long line on the palm of your hand that starts between your index finger and thumb and follows closest to the thumb down to the heel of your hand, It's been an old wives' tale that if that life is especially, if that line in your hand is especially long, it means you're going to live a long life. If it's short, then the news isn't so good. Well, does this really work? The answer, unfortunately, if you've got a long lifeline like I have, is no. A British study showed that there is no correlation, no shared relationship between the length of that line on your palm and the length of your life expectancy. Here we see the question of validity. A variable is said to be valid. It's said to be a valid measure of a property if it is relevant or appropriate as a representation of that property. In this case, we did not have a valid measurement. The length of your lifeline isn't related to the length of your life, so it isn't going to measure the length of your life. When we want to measure trials that are hard to measure, like happiness, fitness, life expectancy, human personality, to name a few, predictive validity, which is what was used in this study, or what was tested in this study, I should say, is the most useful way to say whether our measures are valid. So, if you had a long lifeline, did you live a long life? We'd have to wait until some people's lives passed in order to measure that, but does the length of the lifeline accurately predict the length of your life? Is one way of saying it. That's called predictive validity, if the answer to that is yes. Let's look at another little snafu that can happen with measurements if we're not careful. The next example, a study on customer service found that there were more customer complaints registered at a large local grocery store in the past year than at a small local market. Is it fair to conclude that the local market had better customer service? What would be a fairer way to present the numbers? Well, hopefully you're getting at the point here. Total numbers in themselves or counts mean nothing. We would expect more complaints at the large local grocery store. They have a lot more customers. There are a larger number of people coming through there. We would expect a small number of complaints at the local market. Not many people visit the local market. A fairer way to represent the numbers would be to use a rate. Often a rate, which can be represented as a percentage or as a fraction, is a more valid way to measure than a count. If we knew the percentage of customer complaints that we had at each store, then of course we can make some conclusions about the customer service at each store. We're going to focus a little bit on the errors in measurement. So let's choose a story here or let's look at a story here to kind of help us see what a measured value consists of. You are at the beach and you want to know the depth of water at a sandbar that is just offshore. One of your friends, whose height you know, stands on the sandbar and you measure the depth of the water by seeing how much of his body is underwater. You report that the depth is 4 feet 6 inches. Do you think this measurement is accurate? Would you get the same result if you measured it again? We see the parts of a measurement in this particular example that's given here. A measured value is the true value of the property that's being measured. I'll put that in quotes. Plus bias, which may or may not be known, plus random error, which is beautifully illustrated in this little example. Bias, well, think of a bathroom scale. I happen to like my bathroom scale. It consistently measures 3 to 5 pounds less than the true value according to my doctor's scale. So my bathroom scale is an example of bias. It produces an error in the same direction on every measurement. But that's not true for everyone. My son, on the other hand, feels strongly that we need to replace our bathroom scale. He's a wrestler and is often trying to make a certain lighter weight class to be guaranteed a spot on the varsity wrestling team. So he doesn't like our bathroom scale because it tells him he's only 117 when in reality he goes to get weighed before a meet and he's 124 or 23, and that puts him into a different weight class than he's expecting to be in. Random error, as I said, is illustrated in this story. using your friend as your measuring instrument. Are you going to be able to repeat that same measurement and get the same value if you continue to use your friend to measure the depth of water? Probably not, because you're just estimating based on where the water level falls on your friend's body. So you're not going to be able to repeat the measurement or get the same results by repeated measurement using this particular device. Finally, I hope that you can see from this example that the true value is a little bit tricky and elusive measurement in properties that are hard to measure, especially in behavioral measurement. So this true value, we think that we're getting, that when we get the measured value, we're getting the true value, when in reality we're not. We're getting the true value plus some bias plus some random error. So that true value is tricky and elusive. It is often not known, and especially so for those properties that are hard to measure. Let's talk about some other problems in measurement. A news article says that the percent of students in New York City public schools who read at or above their grade level has increased. Surely this means that student reading performance is improving? Well, not quite so fast. Unfortunately, it's not quite that simple. You must develop the habit of looking at numbers in context, and here we are looking at numbers out of context. If we were to look at numbers in context, we need to ask many questions about the measurements used to justify the statement that was given. If we were to ask some of those questions of this study, we would discover that the school system has just tightened its standards for promotion from grade to grade, holding the poorest readers in lower grades. Notice that they used reading score by grade to measure the reading performance. A little bit misleading here, because by changing the grade in which students are enrolled, you can change the reading scores at will. It would be much more valid in this case to use the reading performance if it were measured by reading score at age, or reading score by age, not by grade. So when reading some of these results that come from observational studies, focus on the measurements, ask the important questions, understand the measurement in the full context of the observational study, which is a very difficult thing to do, by the way, because many times that full context is deliberately hidden because it doesn't really support the conclusions that are being drawn. So let's take just a moment to recap. We're going to fill in some of these definitions again, just to recap what we've picked up in this lesson. A measurement is valid if it is an appropriate representation of the property of interest. Often the rate at which something occurs is a more valid way to represent this measurement than the count of occurrences. Often it's difficult to determine if a measurement is valid, especially for behavioral properties that are being measured. So how can I develop a valid measurement of happiness, or of assertiveness, or of fitness, or of wellness? A measurement has predictive validity if it can be used to adequately predict some outcome related to the property of interest. And remember what errors in measurement are, how they work together. So we have some measured value. Remember, it is the true value plus bias plus random error. What we're really after is only a part of what we get in any measured value. Remember that bias means that each measurement has the same systematic error in one direction. My bathroom scales, which are biased, systematically measure less than your true weight. And also random error, which is another part of the equation, means that repeated measurements on the same individual give different results. I also have a little bit of random error on my bathroom scales. For example, when I weigh myself in the morning, If I don't like the result of what I see, I step off of it and step on it again. I may be a pound lighter, a pound heavier. If I don't like that, I step off, step on it again, and my weight is different than it was the other 2 times. So bias and random error are always a part of any measured value. A measurement is reliable. It's another big term we learned and talked about. If the random error is small, meaning we can get repeatable results. The reliability of a measurement can be improved by taking repeated measurements and using the average of those measurements. So if I wanted a better representation of my true measurement of my weight, I could use those 3 measurements that I described earlier by stepping on the scale 3 times because I wasn't satisfied with what it told me, and average those 3 weights together and say, okay, that's what my true weight is today.